Again, I'm continuing on with my binomial probability distribution example of the number of girls out of 10 births. So again, for this example, n is 10. The probability of success in a single trial, assuming boys and girls are equally likely, is 0.5. And for this example, I want to find the probability of getting at least 6 girls. So that, in probability notation, is the probability x is greater than or equal to 6. At least implies the case of equality. This is not the same thing as saying find the probability x is more than 6. In that situation, the case of equality is not implied. So if I'm looking at the probability distribution table for when x is at least 6, that's going to be summing the individual probabilities from 6 through 10. So it would be the probability x is 6 plus the probability x is 7 plus the probability x is 8, and so on. But a quicker way to do this would be to recognize the fact that if I were to sum all of these probabilities, the sum would be 1. So I could take 1 and subtract out the probability x is less than or equal to 5. The cumulative probability table does the summation 0 up through wherever you need to stop. So we don't have to sum any individual probabilities. We could just jump over to the cumulative probability distribution table and subtract out the probability x is less than or equal to 5. Because the complement to being greater than or equal to 6 in the discrete case is going to be less than or equal to 5. So the probability x is at least 6 is going to be equal to 1 minus the probability x is less than or equal to 5. So it's going to be 1 minus this probability off of the cumulative table. So doing that subtraction, the probability x is at least 6 is 0.377 rounded to 3 decimal places, and that would be the same answer you would get if you were to sum all of these individual probabilities.